Hello friends, welcome to engineering tutorial. So in this video we are again going to take our discussion forward related to electricity and magnetism, and so far we have discussed about the basic concepts related to electric potential and potential difference between 2 points. So in this video we are going to correlate the concept of electric potential or potential difference with the line integral of an electric field. Okay, how we can establish a relationship between the line integration of an electrostatic field with the potential difference. Now so far we have discussed the basic concepts related to electric potential, what essentially it means, okay, and there we established that electric potential basically is the work done on a test charge to move it from one particular point to the other against the electric field. So we discussed that the electric potential at any point, let's say at VA, is the work done in moving the test charge Q0, positive test charge Q0, from infinity to that particular point divided by the test charge itself. Similarly, the potential, electric potential at this point VB, is the work done in moving the test charge from infinity to that point divided by the test charge. Okay, so of course the work done to move the test charge to B will be greater than the work done to move it to A, because B is farther, it is far away. So naturally VB will be greater than VA. This is electric potential at a specific point. Then electric potential in between 2 points, okay, let's say VB and VA. In between points B and A, VB and VA, the potential difference between these two will be the work done in moving the test charge located at A to B, okay, divided by Q0, or that can be expressed as WAB is equal to Q0 into VB minus VA. Up to this we are clear about. Now we will extend this discussion and correlate it with the line integral of an electrostatic field. Now let us assume that we have an electric field acting from left to right, and then we have 2 points A and B, B at a higher potential than A. So here these electric field lines, they are equally spaced and they are straight. So we have a test charge, let's say at A, okay. Now suppose we have to move this test charge from A to B, we will have to do some work. We know that the electric field, okay, electric field is expressed as the Coulombic force divided by the test charge. So here the force acting on the test charge will be this Q0 E vector, okay. So if we have to move this test charge, positive test charge, from A to B, then we would have to exert an opposite force, because we are moving it in the direction opposite to the direction of the electric field. The electric field is acting from left to right, we have to move it from right to left. So here we have to exert an opposite force which is equal to minus Q0 E. Only then we can move it against the electric field. Okay, so now here let's say we have to move this test charge by a small distance, let's say dl. So for that, to move this test charge by a small distance dl, we have to do a small work dw, okay, small work dw, and that dw will simply be, we know work is equal to force into displacement. This is not cross product, this is simple multiplication, okay, like this, force into displacement. Don't confuse it with cross product, okay. So force into displacement, work. So dW will simply be minus Q0E, which is the force multiplied with displacement, okay, this. So in terms of, if you want to express it in terms of vectors, it will be like this, but simply also we can express it. So this is by a small displacement, let's say dl, okay, displacements dl. So if we have to move the charge totally from A to B totally, then we would have to integrate it, dW, that will be WAB, and that will be expressed as whole integration from A to B minus Q0 E vector dl vector. This is the expression, okay. Now if you just rewind, here we established a relationship, WAB is equal to Q0 into VB minus VA, this, and compare it with this, WAB is equal to minus Q0 E into dl. So if we correlate these two expressions which we just established here, then we can see that WAB is equal to Q0 into VB minus VA, and also WAB is equal to A to B minus Q0 E vector dl vector, these two things. So here if we compare these two expressions, then we'll have Q0 into VB minus VA is equal to A to B minus Q0 E vector dl. So Q0 will get cancelled out. So essentially it means the potential difference between points A and B is equal to this, the line integration of the electrostatic field from A to B. This is the relationship that we wanted to establish, okay, the relationship between potential difference between 2 points and the line integration of the electric field in the same direction, okay, this. So this is the important concept which was which I wanted to express, okay, the relationship between electric potential or potential difference between 2 points and how it is related to the line integration of electrostatic field. The potential difference between any 2 points in electric field is the line integration of the electrostatic field between the same 2 points. Now here we have discussed about the correlation between potential difference and line integration of an electrostatic field. Now we will discuss another important concept, which is electrostatic force is a conservative force, okay, in nature. So how we will prove that? So what essentially it means is that the work done, okay, in moving a test charge from one point to the other and again back to the same point, okay, the work done in that is equal to 0, okay. So essentially it means work done in moving a test charge around a closed path, that is returning it back to the same point, the initial and the final point. When it is the same, then within an electric field, the work done in moving the test charge along the closed path, it will be 0. So how it will be? Let's see. Now we know that when we have to move a test charge, let's say Q0, okay, let's say we have a test charge at A, Q0, and we have to move it to B. In that case, the work done will be work done in moving the test charge from A to B, that will be Q0, final potential VB minus initial point potential, that is VA, this. Now the test charge has reached here. Now again we have to move this test charge from B to A, okay, B to A. So in that case, work done in moving the test charge from B to A will be again test charge value by the final point minus initial point, that is VA minus VB. Try to understand, initially the initial point was A, then it reached here, so this is the work done in moving the charge from A to B, final minus initial. Again, when we have to move it from B to A, the initial point is B, final point is A, so that's why VA minus VB. Now if we add these two, WAB plus WBA, it will be Q0 VB minus VA plus Q0 VA minus VB, which will be simply equal to 0, okay, it will be 0. So this proves that the work done in moving a test charge from one point to the other and again back to the same point, that is when the initial and final point they are the same, then the net work done in moving the test charge is 0. So here also we can conclude it in a different way, which is that the line integration of an electrostatic field around a closed path, okay, the line integration of an electrostatic field around a closed path is 0. So here we concluded that potential difference is the line integration of the electrostatic field between the same 2 points. So here, as the work done is 0, we can say that the line integration of an electrostatic field around a closed path, it is 0, okay, that is 0. This is another important conclusion, okay. So here we have discussed about the relationship between electric potential and line integration of an electrostatic field, and also discussed about the nature of electrostatic force, that it is conservative in nature, that is work done in moving a test charge around a closed path in an electrostatic field, the work done is 0. So line integration of an electrostatic field around a closed loop or a closed path is 0. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.